Certainly.
Okay, away you go.
Hello, and sorry.
Go, carry on, Pete.
Hello, and welcome to our webinar. I'm Pete Starkey, a member of the Council of the Institute of Circuit Technology, which is dedicated to technical aspects of printed circuit board manufacture and assembly. The Institute continues to successfully provide its members with opportunities to improve their knowledge of manufacturing process technologies, materials and practices, and to stay in touch with current and future developments. The future of printed circuit manufacturing and assembly will rely heavily on automation and the establishment of the smart factory. What will this involve, and what additional skills will engineers need to learn? A leading expert in this area is Happy Holden, Honorary Fellow of the ICT, who has kindly offered to deliver a series of 8 one-hour webinars based on his recently published ebook, 24 Essential Skills for Engineers, which is free to download from the iConnect 007 website, and which will form a valuable resource for in-house training of engineers and their career development. Happy gave his first presentation in the series, Automation and the Journey to Your Smart Factory, on Wednesday last week, which introduced the elements of the journey and discussed the key issues: who, what, how long, when, and how much. His emphasis was very much on avoiding factory automation consultants who will generally charge you for learning your processes and procedures while selling their own equipment or software. Instead, Happy suggested that you select your own engineers who are familiar with your own processes and procedures and let them learn how to do the automation planning. Then they can teach others this essential skill, which the factory will need over and over again. Today's presentation, the second in the series, is focused on the following skills: total quality control, Six Sigma and statistical tools, problem solving, and design of experiments, predictive analysis. If you have any specific questions, please direct them to happy@iconnect007.com. So it gives me great pleasure to hand over to Happy Holden. Happy.
Good, thank you, Pete, for the great introduction. It's really useful to start out with our eminent spokesperson there, Pete Starkey, who I had the pleasure to work with for many, many years. If this series seems a little jumbled and awkward, forgive us, because we're not. This is the first time we've ever put this together. You're the first people ever to kind of hear the totality of all of this. And, the ICT is, not a for-profit type of training institute and things like that. We're all kind of amateurs trying best as we can provide our insight and knowledge for your use. We will, being recorded, we will continue to improve this series. So check back periodically to the ICT to see what we've added to it or what we've improved. I can't emphasize enough, though, to download the ebooks, the 3 ebooks from 007, the NIST Engineering Statistics Handbook, because that might go away at any time, and then two other ebooks of your own choosing, essentially about programmable logic controllers, PLCs. I have one that I use that reference there. And then books about sensors from Instrument Society of America or somebody like Keysight provide that additional insight that we have here. All told, if you do the reading, you will find these are basically introductions. I'm spending in this series 20 minutes on particularly important skills that are part of the automation methodology. But that's only 20 minutes. For me, these topics and skills were either a 1-day course, a 3-day course, and many times a 5-day course. So this does not, could not be considered the total training on the subject. Hopefully enough to introduce to you the importance of going on your own and continuing to study some of these factors. I've kind of arbitrarily put it together to handle a number of the important skills and then into the automation elements and the smart factory elements in the middle, and then finishing up with additional tools. They all are part of the overall process. And so let's get started and start talking about it. I've been in the business since 1970 and been an engineering manager since 1977. I was recruited by Hewlett Packard directly out of the university, specifically because of my university focus in the area of not just processes, chemical engineering, but the focus on computerization and the work in electrical engineering, computer science. I was fortunate, like I said, to be recruited by Hewlett Packard, which I didn't know that much about. I was looking for employment in Dow Chemical or DuPont or Exxon or Mobil, one of the traditional ones. And Hewlett Packard was looking for someone with a process engineering background for their semiconductor area. With this, and it was also fortunate because I started with a relatively small company. Hewlett Packard only had about 2,000 employees and 200 million in sales. But by the time I retired, they had 156,000 employees and were $55 billion. But even then, we were quite highly diversified. Like I said, during my time there, Hewlett Packard had expanded its product line to 25,000 different products with 21,000 options, being manufactured all over the world. In terms of, we had 5 printed circuit shops around the world with 55 through-hole assembly facilities, growing to 11 printed circuit shops and 37 SMT centers. So recruiting the engineering, building these facilities, and equipping them provided a lot of experience for me. My last management position was Chief Technical Officer of the world's biggest printed circuit organization, which most people don't know about, High Precision Industries, better known outside of Asia as Foxconn. And at Foxconn, I went from, working with the smaller printed circuit manufacturing and assembly to one that's absolutely dwarfs everything. Just one of my sites had over 20 million square feet of printed circuit manufacturing floor area. And that was only one of 6 different sites in Taiwan and China that Foxconn had. But Foxconn being quite a bit different Foxconn is a captive manufacturer. It's not in the really the merchant, and consequently always slid under the radar. And so, going from prototype and quick turn also to extremely high volume was an interesting learning experience. So we're going to talk about three of one of the most important parts of essential skills. These are all an important part of setting up the smart factory and also setting up the business objectives and goals for automation. And these are, you've had your homework reading assignments for the chapters of this that are in the book. Hopefully, if you haven't downloaded, be sure to remind yourself to download it and read it, because I'm summarizing the chapters in 15 to 20 minutes. So there's much more illustrations and informations in the particular chapters for you to go after. And so my kind of number one is total quality control, also called total quality management. This is one of the foundations of any kind of manufacturing, and one that I spent a lot of time in Hewlett-Packard learning. It's interesting that we were training everybody, design engineers, manufacturing engineers, production workers, in the whole total quality management, which was started when actually Dr. Deming personally hit off the program at Hewlett-Packard. He did that, provided every executive and the president of the company sat in the front row of his course. And because Deming very much believed that these programs are top-down driven. And now, like I said, all of our executives were in the front row of the auditorium. As a junior engineer, you might say, I was kind of in the back of that, but nonetheless, got a chance to listen to Dr. Deming personally, focusing on this. And so today, we'll talk about total quality control and another way of looking at that Six Sigma methodologies. And then some of the statistical tools and curve fittings and design of experiments. So total quality control is a management operation philosophy committed to quality that focuses on continuous process improvement using data and the scientific method, making it perfection a goal. It requires universal participation by everyone, everywhere, working as a team so that the results is customer satisfaction, where expectations are consistently exceeded for both internal and external customers. The simple little flow chart, focusing on customer satisfaction and quality leads to improved market share, decreasing in prices and costs, improvement in profits and profitability. And that, I found this essentially to be true. So total quality control is not a new program. It's basically a management philosophy and an operating methodology requiring breakthrough thinking rather than doing things the same old way that we've always done them. It's a structured discipline approach to identifying and solving problems, developing new technology, and institutionalizing the improvements gained from those disciplines. It's not just firefighting, or hopefully will replace firefighting. It's conveyed by actions of management. It's not just conveyed by slogans and posters. In other words, it's basically top driven and top side down. So it's a top down focus rather than bottoms up. It's a long-term focus rather than short-term. And it's supported by some of the QC tools that we'll talk about today. And this is one reason why TQC hasn't necessarily catch on, because It's not something where you send an engineer or supervisors to a course trying to get this thing from a bottoms up. This really is a tops down methodology. Like I said, Deming would not show up to start the program off if the president of the company and all the vice presidents and executives were not in the front row through the entire program. And not just to follow that up, but we used a methodology in which to teach total quality control and management. It started with our president, who actually taught the course to the executives, which is really 5 days, kind of half day. And then for each of those executives, each were given a project individually, mentored by the president himself. And then each executive taught the course to his staff and the ones below, and then mentored a project, so that eventually every person would deal with this material 4 times. Once as the student, and then the project, then as the teacher, and mentoring the projects. And finally, from our tops down methodology, it finally took hold. And it essentially took hold because you realized that expectations were set by your boss. They weren't bottoms up when you're trying to convince your boss how important this total quality control was. No, just the opposite. Your boss was teaching you how important it was. And so expectations totally got changed. And until you have that kind of management commitment and management philosophy, a lot of times these quality programs just won't stick and won't be effective. So management commitment is really important here, as well as a customer focus on what you're doing, the continuous improvement, and employee empowerment, and everything being fact-based decision-making, focused on process improvement. So the tools for data analysis and display, I'll go over next, are cause and effect, histograms, Pareto, pie charts, scatter diagram, spider diagrams, flow charting, cost benefit analysis. But there are also in this tools for generating ideas and information, brainstorming, mind mapping, check sheets, interviews, and tools for decision-making consensus gaining, weighted voting criteria reading, paired comparison. So these are the fundamental TQC tools that you learn in total quality control in terms of process flow charting, fishbone diagrams, also called Ishikawa diagrams, histograms, Pareto charts, correlation, and control charts and control thing. So these tools are not a substitute for good judgment or process knowledge. They aid to help convert data into information, which can then be used to make objective decisions, and indicating problem areas or unnecessary loops or complexities, and where simplification of process is possible. Cause and effect, the Ishikawa or fishbone diagram, are useful to organize potential factors that produce an observation, be it customer satisfaction, yield improvement, defect elimination, or productivity. Histograms and Pareto charts are different methodologies of showing the distribution of the measured data, and also prior specification of the specific frequency or the variable being talked about. Control charts show the level of statistical control, the predictability of a process, and when it hits upper and lower control limit actions. Correlation plot shows a relationship of 2 or more variables, and it should be done on single items, not averages. Statistical process control, which this begins to focus on, helps show the out of tolerance situations, or the process being unpredictable or unstable, so that a stable process, over time, works within the predicted distribution of that. An unstable process may, over time, move in and out of the what's defined as a stable process. And so, in control, specific causes are eliminated from looking at an out of control process, or the process capability thing, in terms of upper or lower, so that a process may be in control, but it's not capable, because the variation from common causes are excessive. If you look at, using this for process improvement, then you kind of go through a specific stepwise function of focusing and choosing, selecting the issue, creating an issue statement, producing a flow chart proposed, selecting process performance measures, using cause and effect analysis in a fishbone diagram based on that, and then using the different TQC tools to collect data for the strategy, analyze it, look for interactions, and put together the required action. This is similar to Six Sigma's competitive analysis, in which improving quality and producing products and services, leads to higher profits and improved revenues and improved market share. A little bit different than the TQC, but it's basically still the same focus on that. The key elements of Six Sigma, which is a specific one, is a process orientation, but also a customer focus, and that data, is collected and used to produce measurements and focus. And the focus is on variation reduction, or having a Six Sigma response, using statistical rigor and process improvement methodology with the bottom line. So, Six Sigma has that 3 dimensions, again, led by senior management, enabled by quality teams, and driven by customer needs, the methodologies, and then the tools in order to achieve business objectives set up by the organization. And total quality management and Six Sigma methodologies are numerous. In the skills ebook, I've highlighted some of the chapters, but you can see that Six Sigma and TQM is much larger than just what I outlined in my essential skills. And that's one reason why it's useful to spend the appropriate time over the years, maybe each particular year, learning an additional skill within this methodology. One of the biggest methodologies and the most important is problem solving. And so both TQM and Six Sigma have the plan, do, check, action, and DMAIC methodology. There's also the 8D planning, the 7-step solution, and lastly, the Kepner-Trago action sequence, KT. This is one that TQM uses, that's basic, is plan, do, check, action circle, useful in terms of setting up goals and targets, setting up the improvement plans, the success parameters, education and training, checking for that, and then actions to standardize this. Within this, there are problem identification and problem analysis tools. And these are some of the ones we've talked about before in terms of flow charts, cause and effect diagram, or scatter diagrams in terms of identifying a problem or analyzing a problem. The DMAC from Six Sigma talks about defining the identity and the state of a problem or objective, validating the practical problem by collecting data, measurement, analyzing the data, confirm and test a statistical solution improvement, and convert the statistical solution to a practical solution control, DMAIC. There's another put out by the Department of Commerce that was the 8-step D1 through D8. That's basically the same process with slightly different definitions, but setting up a team, describing the problem, developing an interim containment plan, determining identity and verifying root causes, choosing and verifying permanent corrections for the problem, and then implementing and validating corrective actions and taking preventive measures, and then recognizing the effort of the team. This also matches the 7-step problem-solving methodology that sometimes they use in terms of, define the problem, clarify the problem with the current situation, identifying and verifying the root causes of the problem, cause analysis, developing a plan to eliminate the root cause of the problem, checking the results, modifying the process of systems to standardization, and then evaluating where we have been and where we want to go next. My particular favorite is a result of a 3-day course I took from a company called Kepner Trago, so that it has a trademark, that focuses basically on situation appraisal, problem analysis, potential problem analysis, and decision analysis. This is very useful because the Kepner Trago action sequence is very useful. This actually is a copy of a little plastic card that I have with me. I took this course in the mid-70s and still have that card and use it today in terms of reminding of, of the steps in a problem analysis, the deviation statement, specifying what it is or is not, developing possible causes, testing of the probable causes, and explain it is or it is not, and verifying the data, and then moving on to decision analysis to choose a course of action, establishing the objectives, classifying the objectives in terms of wants and limits, generating alternatives, and comparing and choosing, what fits and doesn't fit. And then also at the same time, doing the potential problem analysis to assure success of the activity in terms of the action plan statement, anticipating problems, anticipating likely causes and their probability, selecting the action, and then providing information. And so one of the things is, especially in printed circuit manufacturing and assembly, is this curve that I developed, in that this is a thermodynamically related process curve. In other words, the performance measure goes from 100% or perfect down to 0. And if the solid line there is our current process, if we can move from the solid line by a process improvement to the dashed blue line to the right, then whatever our problem is, or whatever the process is, we move from 2' to 2, but with the new process, we move up in performance to 3. At the same time, if we can have feedback to printed circuit design in terms of best practices, how to improve the printed circuit board for manufacturability, or many times what we call design for manufacturing and assembly, then instead of 2 to 2', our product can be simplified. In other words, we move to the right, and so you would go from two down to the 2' by simplifying the product. So there are two elements: the product improvement and the process improvement. The process improvement is what manufacturing provides, but analyzing the cause of data and yield loss and simplification can lead to product improvement. And that's a very useful tool as a feedback to improve not just your performance, but that of your customers and like. So that depends on statistical tools. And design of experiment is a very important methodology, and it's a series of well-established statistical approaches to addressing challenges over a wide range of discipline. Design of experiments was basically created out of World War II and the use of agricultural statisticians working for the government. But design of experiments is a typical method that can be used to not just solve root cause identifications of issues, but also for process optimization and assessment of inherent robustness of response, which in the new smart factory is now being called a digital twin. So in 1990, the National Bureau of Standards, the US government, was distributing a popular statistical document called Handbook 91. That was replaced, and with response to Sematech, the semiconductor consortium, they created a new web-based statistical handbook, including statistical software called the E-Handbook of Statistical Methods. We call the Engineering Statistics Handbook. This is one of the best handbooks and softwares designed for process engineers such as those of us in printed circuit fabrication or electronic assembly. And this is not like a university text where they focus on the mathematics of statistics. This is one of the best books written for a working process engineer. And so you'll see that, look at some of the chapters, but also to make this usable for everybody, it's available in 7 different operating systems, as shown there in the bottom. Because I don't know how long this is going to be available on the internet for free, I encourage everybody to download the Engineering Statistics Handbook and the software. And I caution you about printing it out. The Engineering Statistics Handbook is 2,800 pages. It's designed to be a hypertext reference document. It's not really a printed book, unless you're used to carrying around 2,800 pages. It's much more useful because of its hypertext ability on a tablet or a simple slate PC for review. Now, I'm talking to you about now. This is not how I started. My computer tools when I first started to 1970 to 74 was my slide rule from college. Yes, I went through college with a slide rule. The reason is because down here at the bottom, I helped design the HP 35 and 65 calculators you see at the bottom in 72 and 74. But until I had these machines, I did most of my work by writing programs in BASIC. And I had to use a microwave network analyzer, basically because it had the paper tape reader printer built into it. And had a nice big display that I could use for graphics. And this is made from a mini computer, the Hewlett-Packard 21 15, which shows the typical multi-layer there in the middle. But I also had sometimes the 64-bit computer with paper tape reader, the HP 9100B down there, which, interesting enough, is the world's first portable computer. Even though it's a 64-bit computer, we had to call it a instrument controller because in 1968, when this device first came out, 64-bit computers required an air conditioning plant and were the size of a small house. And no one would believe that you could make a 64-bit computer the size of a typewriter, as it's seen in the middle. So we called it an instrument controller, but it's a full 64-bit computer that I used. Typical of design of experiments was this program I wrote in 1970 in BASIC using the Plackett-Berman design for experiments. This particular one was focused on electroless copper voids. And this shows a little bit of the 96-line BASIC program and the program output from having to write the software. Today, you have the ability of the semiconductor handbook and all of this software being available for you free of charge to download. But when I started, that wasn't the state. And we had to do this our own if we wanted some of the work. So the NIST Sematech e-handbook of statistical methods is an excellent, not just handbook, but it provides examples and tutorials so that if you're not familiar with any of the statistical technique, that's okay, because they start out with the very basic assumptions and provide, areas of like selecting the right statistical tool, in terms of measurement analysis system, or you want statistical process control, or method comparisons, or design of experiments, which I'm talking about. And are the factors in the design of experiments qualitative only, or not all of them are qualitative? Here's what you'll see if you go to this particular URL I provided there. Unfortunately, you cannot go to nist.gov and find this any longer. About 10 years ago, other topics took over the website in terms of the main menu, but it's still within the website. Again, I emphasize, please download it and download the software as soon as possible, because there's no guarantee, how long that'll continue to be available for free. But one thing you can see there in the handbook chapters are, the first chapter is not about mathematics. It's about, do you have a problem? Exploratory data analysis. And the 8 chapters moves you through how you would solve the problem in terms of measurement of process characteristics, measurement of production process characteristics, process modeling, process improvements, and then process or monitoring control, and product to process comparisons, and finally, assessing product reliability. In other words, if you think you've solved the problem, great, but have you, in creating this solution, created a reliability issue? So this is quite a bit different than a university course at all, in terms of how it focuses on the working engineers such we have. Like I said, this, and in the same case, each of these chapters provides a case study, an example, a set of data, so that it takes you through using the software that you can download on your computer, and then gives you the feedback, and then encourages you to add your own data and your own variables into that, and then discusses the results. So this is very much an interactive and self-paced method of learning. statistical tools in an excellent fashion. And I first came across this about 25 years ago, looking for a way to assess Weibull reliability data. One of the things is because I didn't have a way to plot the unusual looking Weibull reliability data, and went looking for it and came upon this chapter 8, trying to figure out what have I found myself here, and eventually backed out to find that, an entire set of software and a book and a handbook available to provide a lot of insight that I hadn't had at university training. Now, an important part of that, I also found in doing this, is curve fitting and correlation, which again is an important tool to help you establish the model. And this set of shareware software that's right here called Curve Expert is interesting because it provides 30 different regression models there in the upper right-hand corner already set up. So once you put in the data and save it, it'll show you the interactions and the regression analysis of different models. The model that I'm showing right here is one of my favorite. This is the defect density model in semiconductor. The interesting thing about the defect density is it's the same model that governs printed circuit defects. So it's very, very useful in correlating independent and dependent variables of a particular printed circuit, and that's the Weibull model. But you can also enter your own models into this. Extremely useful, and because it's pre-set up, many times I go to this before I go to the data plot one that's provided. So design of experiments is, fortunately or unfortunately, one of the ones that you might get at the university, but many times in my particular university, I was able to have a chemical engineering course on this, but the next year they dropped it because of the need to add other courses for the engineering. And so this is what I consider one of the most expensive, important of all tools. And the reason is that many times what we're doing in printed circuit or assembly really involves a black box. In other words, we're providing the inputs and we're looking at the outputs, but the transfer function and what happens inside that black box is not necessarily something that we understand. And there are controlled and uncontrolled variables involved. Now, the interesting thing about engineering is when faced with a problem, that I found is that engineers many times have the wrong first action. The common sense approach is always recommended as let's hold everything constant and change one thing at a time. Well, this technique is fast and cheap when it works, as it often does for confirming single or independent factors whose presence can be logically suspected. The biggest problem that I found in electronics manufacturing is that the independent factors we're looking at are the quantitative factors, grams per liters, temperatures Celsius, et cetera, et cetera. Those variables that we've been told are important and that we should control. And so we have a tendency to jump on them first. What's more likely to happen in the real world is that the qualitative variables are involved in this. And the qualitative variables may be winter versus summer. It may be first shift versus the second shift. It may be machine 1 versus machine 3, or tank 1 versus tank 3, or who did the maintenance or failed to do the maintenance. It's not a quantitative number like degrees Celsius or RPM. It's qualitative. And because there can be many, many qualitative variables that are involved there, holding one factor, changing only one factor at a time will not find the solution because you're not looking at the entire problem. And that's where you get into factorial design of experiments. The number of factors. If there's, one factor, it can be solved by common sense and things like that. But what if there's 2 to 4 or 5 or more factors involved, both quantitative and qualitative? And you get into what we call full factorial designs, or centered designs, or fractional factorial designs, and even evolutionary operations. That's one reason why in some of the problems that I was initially faced with, I had 5 or more variables. And so I needed a Planck-Berman methodology. And to get that, I had to actually write the program in BASIC so I could run it on the HP computer, because I didn't have anything else available, and I wasn't at the university anymore. So the fractional factorial design is really for screening, because you notice there that the level that we're setting these 3 variables at, even though they're at 2 levels, there's matrices that are eliminated. And so this looks at interactive effects, but not at, and which ones are the most significant. After we've whittled this down to 3 or fewer variables, we may go to a full factorial design interactions, because now we can check for interactions and detailed analysis, or even one with a centered design to have 3 levels, so we can check for linearity and nonlinearity as well as the interactions. An example of this is one of my early problems on the interlayer registration for capacitive coupling for the ROM memory. Remember I told you about the world's first portable 64-bit computer in 1968 there. This whole machine, even though it's 64-bit, did not have a single integrated circuit in it. In fact, you can see there the enormous number of transistors involved. But even more important, in 1968, we didn't have ROM memories. And so this has the world's highest density physical read-only memory ever put together. It was a 16-layer Teflon multi-layer there inside the red circle. And it was made up of these, inner layers with these comb patterns, and the comb patterns produce the 1s and 0s. And so having this set of comb patterns on the back side of the core of the inner layer, they would run a high-speed pulse. And as the pulse went down the chain, depending on the opposite side of the prepreg, there is either a copper or no copper at all, and you get a 1 and 0 with an op amp at the end of it. So when you turn this machine on in 3 minutes, this thing entirely loaded the 64-bit operating system and everything else. And then the variables, once it was run, was core memory based, but the read-only memory was this. Now, the problem was 1970, this 16-layer ROM memory was 0.125 millimeter traces and spaces. Well, we were doing essentially 15 mil lines and 35 mil spaces, and this was 5 and 5. And so we had to utilize semiconductor photoresist and a number of other techniques in order to make this thing with any kind of yield, and especially with having to deal with Teflon layers involved in that. Another example early on was looking at the difference between the industry best practice of a slot centerline system versus drilled an X-ray tooling hole methodologies. And so another variable on this, not just the methodology, but the method of venting, either no venting or copper venting. And so this is kind of a full factorial design of 3 variables at 2 levels, whereas the response is the image shift in microns of the particular targets within there, whether or not we had venting or didn't have venting, the tooling poles, and then the actual pressure. So you can see that, yes, there's a quantitative variable in terms of pressure, but you've got 2 qualitative variables in terms of tooling, method of tooling, and venting. And this is the reality of today's modern manufacturing. You know, it could be man, it could be measurement, it could be the machine, it could be the environmental factor, it could be who you bought the chemicals from, it could be storage life, it could be maintenance. All of these potentially are interacting in your manufacturing process. So having the tools to categorize and work with them. Oops. And so, you know, and so for the 8 experiments, you know, these are the tooling, vent, and pressure, T, V, and M. And that, you know, this are the particular order of tests and results in terms of shift in microns of the experimental we're doing. And the response of the interlayer shifting in a multi-layer PC board. This is circa 1972, 1973. So it's pretty old, but yet it shows significantly how we were able to improve productivity and improve quality even back in the early 70s by the use of these tools that had been developed during World War II. And the statistical handbook will help you go into the interpretation of the interactions in terms of main effects, 2-factor interactions, and 3-factor interactions in terms of now the advantage of this is that this will allow you also to produce an equation that models this performance and results. The beautiful thing about that is that these equations also can be turned into digital twins. And so for the smart factory of the future, you can use this design of experiment methodologies to help you create the models that allows you to predict what's going to happen outside the parameters or things like that. And we'll talk about that a little later in the lectures. We're talking about the automation methodologies. With that, thank you for your time. It's a lot. That's why I encourage everyone to read through the chapters in the 24 skills, but also to download the NIST Engineering Statistics Handbook and read the first chapter in why the NIST Semiconductor Handbook was put together, and how this will help you in your pursuit of process improvements, problem solving, and improvement in the print circuit and assembly world. With that, thank you for your time today. And we'll be back here next week, same time, same station.